Hey everybody, today we are going to be looking at chapter 6. We've got two videos coming. The first one is an intro, basically covering 6.1. And in chapter 6, we're going to be looking at the difference between two means. In chapter 5, we compared two proportions. Now we will look at two means for quantitative data. So we're looking at mu1 from population 1 or group 1 versus mu2 from population 2 or second group. So we'll be looking at the difference between the two means. So the hypothesis will be set up. The null, always that there is no difference, or you can think of it as they are the same. But what we want to look at is the difference, because we need a value to take forward in testing the samples. So the difference between the two population means is 0 or no difference. That will be our null. The alternative is one of the three inequalities that we've been working with. So we have the difference will be greater than 0 or a positive number if mu1 is greater than mu2. The mean from population 1 is greater than the mean from population 2. It looked like this if it were written as an inequality. If we subtract them, mu1 minus mu2, then their difference will be greater than 0. Or mu1 minus mu2 is less than 0. If mu1 is less than mu2 and I subtract in this order, we'll have a negative value because mu1 is smaller than mu2, written like this as an inequality. So when you subtract them, when you find their difference, it will be less than 0. Or we can simply just say that they're not equal to 0. The difference is going to be different. Their difference is going to be 0, or they're simply just different. We're not claiming one is bigger than the other. So just remember, now we're looking at the difference between the two means. The distribution of these differences. So we have the two populations. We've got mu1 and sigma 1, or mu2 and sigma 2. That's the mean and the standard deviation from the two populations. We get samples from both of those populations or both of those groups, and then we'll have the statistics from the two samples. So I have sample mean 1, standard deviation, sample standard deviation, and then the sample size. And then the same here from group 2. Okay, so when we assume that the null is true, meaning the difference is actually 0, the distribution of all of these differences, so I keep taking samples, finding the differences, plot them. Take samples, find the difference in the means, plot them. And I continue to do that. Keep plotting all these differences in sample means. That distribution of all of those differences is going to be normally distributed. It will be centered at 0, meaning the mean of all of these differences is 0, which, remember, is always the case. It's the same as what we are claiming in the null hypothesis. We're assuming that that is true, so the average of all of these differences is 0. Now, the standard deviation of this sampling distribution of differences, again, it's we've got two populations now, so I'm going to take in both of the standard deviations from the populations. If these values are known, the standard deviation from the population, we use them. So it's the standard deviation squared, which, remember, the standard deviation squared is just the variance. We call that the variance. So we divide by the sample size. So we take the standard deviation of the first population, square it, divided by the sample size, plus the standard deviation of the second population up here, squared, divided by the sample size, and then we take the square root of that sum. Again, normally we don't know that standard deviation of the population, so when we substitute the standard deviation of the samples in place of the standard deviations of the populations, we have what we call the standard error. It's a good estimate of the standard deviation of this sampling distribution of differences. We're going to use this maybe once, but our applets will calculate this for us most of the time. So when we do our hypothesis testing and we want to find some significance, if the difference that we're observing is significant, the other thing we can calculate is the standardized statistic. Remember, that's kind of looking at where does our observed difference fall in that null distribution that we were just talking about from 0, because 0 was the center of that null distribution. So where does our observed difference fall compared to 0? And then you divide it by the standard deviation of the sampling distribution. And when we were talking about means, we're talking about the t distribution, that family of curves that depends on the sample size and degrees of freedom. Now we will see in the applet degrees of freedom, but we are talking N1 and N2, the two different sample sizes. They do not necessarily have to be the same. So calculating degrees of freedom when you are comparing two means is a little trickier than just a single sample. So we will actually just let the applet calculate that for us, because it's far too complicated for this intro to statistics course. Okay, so we can also use the theory-based approach if the conditions are met for the central limit theorem. Recall that the sample size needed to be at least 20 when we had a single sample mean. Well, now we just need both samples to be at least 20. Or you could have a normally distributed population for both of them. And then you could also use the theory-based approach. So one of these two things has to be true in order for us to be able to just use the theory-based approach. We will also look at confidence intervals. Remember, confidence intervals are a way of estimating our difference. So here's our observed difference, and then we simply add and subtract the margin of error. So we'll get a lower value and an upper value, and that'll be our range of values that we are estimating as the true or actual difference in the population means. That's what our confidence intervals are all about. All right, so we're going to get started with the first activity here. And in the first section, 6.1, we're going to be just looking back and doing some exploratory data analysis. Remember, we're working with quantitative data here, so we're going to be using StatCrunch. Okay, we're going to look at shape, we're going to look at the center, we're going to look at the spread and the variability, and we'll check for some outliers. Okay, so let me bring up my computer here. The first example that we look at, we're going to go back to our Old Faithful data, except now we're going to be comparing 2 years, the time between eruptions in 1978 versus 2003, okay? So the question we're considering here, were the waiting times between eruptions similar or different in the 2 years? Were the times between eruptions more consistent in 1978 or in 2003? Or were they similar? Were tourists more likely to wait longer in 1978 or in 2003? So these are some of the things that we're going to look at when we are exploring this data. So we're going to go to StatCrunch, and I'm going to open it up. It's called Old Faithful, Part 3, 1978 versus 2003. I'll bring it up on the screen here in a sec. The observational units that we're looking at are the eruptions of our Old Faithful geyser. Okay, so 2 variables in the table that we will be looking at will be the year and the time in between eruptions. Okay, we looked at this earlier in the year. So if I come over here to my StatCrunch, okay, so bringing up StatCrunch. There's our group. Click on that. And this is the first data we looked at earlier in the year. We're not looking for that one. I want Old Faithful Part 3. So I'm going to go to the next page. There it is. Old Faithful Part 3, 1978 versus 2003. Click on that. There is our data. Okay, so you can see we have the year. Let me see if I can get this worked out a little bit. And the time in between eruptions. The year and the time in between eruptions we're looking at. So we're going to be doing some exploratory data analysis on that. So remember that the observational units are located in the rows, okay? The observational units. This is one particular eruption in 1978. I had to wait 50 minutes before I could see that one, and so on. So that the rows contain our observational units, and then the variables, the year and the time in between eruptions, are in the columns. Okay, so when we are comparing 2 groups in StatCrunch and our observational units, you can see if I scroll down, I'm scrolling down, and somewhere, okay, right here it turns to 2003. Okay, so I've got the 2 groups I'm going to be comparing, obviously, are the 1978 versus the 2003. So when we do this in StatCrunch, we have to use a option called Group By. So everything we're going to be doing here, we're going to group by year. So we're doing our analysis on the time between eruptions, but we're going to make use of the group by year option in all of our calculations that we do. So the first thing we're going to do is we're going to bring up this dot plot. Now it's already on your activity. Let me just kind of show you right here. I'm on page 2. So, but we're gonna get this ourselves as well. But when you're done, this is what yours should look like. So there's group by feature in our commands. So I'm going to go to graph. We're going to get a dot plot. I'm going to select the time, but right here it says group by. You see that? Group by. So click on that, and I'm going to select year, and then just come over here and compute. And there's my 2. I'm going to stretch it out a little bit, bring it over here in the center. There is my 2 graphs. The year 1978 is on the bottom, and then 2003 is on the top. Now I want to put them together on the same graph so that they are on the same scale of time. So if I looked at 2 separate dot plots, it would be hard to compare them because they're probably going to come out on 2 different scales. So I want them on the same scale so I can easily compare them. So does that look like what you have on your paper? Now, if I have this not quite as, if I condense it a little bit more, notice how some of the dots kind of jump over into one column because I'm condensing my graph. So I want to make sure this is nice and stretched out so that we have pretty much the same thing you're looking at on your paper. All right, so now we're going to analyze the shapes. We want to look at the difference in the shapes. What is one difference that you see? So in 1978, it looks like the values are a little bit more spread out than in 2003. Okay, so there's more, a lot more less frequent waiting times in 1978 than there is in 2003. Remember, the time here is the time between eruptions. So we had to wait less time for the next eruption in 1978 than we did in 2003. The center of each of them, well, I can go ahead and I'm going to go ahead and get my my measures here for center. So I'm going to go to my summary stats, columns, and I'm going to bring over my variable I'm interested in, time. Again, I have to do group by year. Otherwise, it's just going to take all of them. All right, I want to get the average. I'm going to get the median. Let's see, there we go. I'm just going to get the mean and the median for center. Okay, so I need the group by, otherwise it's not going to give me each individual group. I want the mean and the median for 1978, and then the mean and the median for 2003, so I can compare them. So there they are. Let's bring them over here so we can see them. All right, so there's 1978, the mean and the median, and then 2003, the mean and the median. Okay, so it looks like in general here, using my proper notation, X bar, and then I just did sub 1978 and X bar sub 2003. And I've got the mean of each of those rounded to 2 decimals and the median for each of those. So it looks like tourists generally waited a shorter time for the next eruption in 1978. They had to wait longer on average in 2003 for the next eruption. All right, now for variability, we're going to get the standard deviations. Okay. So just looking at the dot plots, looking at the 2 dot plots, okay, which distribution do you think has more variability? So if I just kind of remember, range is also a measure of variability. So if you look at 1978, we go to, like, maybe that's a 41 or a 42. It's a 42. If I put my little mouse over it, it tells me all the way to 95, 42 to 95. And in 2003, it goes from 56 to 110. So it looks like 1978 is a little more spread out than 2003. They vary a little bit more than in 2003. Okay, so we could do that. And then actually in the next page right here, it's asking for the standard deviations on the page 3. Okay, so looking at that, I'm going to close this one out, and I'm going to go back to my summary stats, columns. I'm going to get my variable time. Again, I need to group by year, and then I want the standard deviation of both of those. So compute the standard deviations, and 1978 we had 12.93 if I round it to 2 decimals. And in 2003, I have 8.46. So that's minutes between eruptions. So 1978 standard deviation is quite a bit larger than 2003. So the waiting time was more consistent in 2003 because the wait times on average were only 8.46 minutes away from the mean wait time. So on average, we had to wait less to get to the next eruption. They were more consistent, meaning we had to wait a little bit longer. If I look back at the averages, the average in 2003 was like 91 minutes about, okay? But you can see more of the eruption times in between were closer to that mean of 90 with a few stragglers over here, okay? But if you end up on this end, you just wait less time for the next eruption, okay? Whereas the average in 1978 was around 71, but you can see there's more data, it's spread out more, okay? So in 2003, we were more consistent than in 1978, even though the average time was smaller or shorter in 1978, it was not as consistent as 2003. All right, so now we're going to go and get to the box plots to look for the outliers. So graph, box plot, time. I still need to group by year, and I want my boxes horizontally. So compute, and there's my box plots. Let me bring them over in view. So do we have some outliers? It looks like in 2003, I have 2 outliers, and I can get those on my computer by just hovering, or I could come over here and sort and find them that way as well. They're on the lower end. So I've got 56 minutes and 58 minutes in 2003 are outliers. 1978 has no outliers. Okay, so the other things we want to look at when we're looking at the box plot, which distribution has a smaller IQR, inner quartile range? Well, remember that the inner quartile range is the difference between the quartile 3 and the quartile 1. So basically, it's the length of the box, because the beginning of the box is quartile 1 and the end of the box is quartile 3. Beginning of the box, quartile 1, end of the box, quartile 3. That is our inner quartile range. So if you hover over the box plot, it actually gives you that inner quartile range. Oops, I made it go away. So here we have 11, and you can see that box is a bit shorter than the one in 1978, and its inner quartile range is 21.5. And it's quite a bit longer than 2003. So remember, inner quartile range is also a measure of variability. So in 2003, this is 50%, the middle 50% of the eruption times in between, right? Whereas in 1978, they're a lot more spread out, that middle 50%. So 2003 has the smaller interquartile range. So if a distribution has a small interquartile range, does that mean that the distribution has more variability or more consistency than the other? So a small interquartile range would mean that it's more consistent. This is more variability, a larger interquartile range. So again, 2003 has more consistency. So this next thing right here that we're going to look at, I'm actually going to go back to my activity here and do this all on that. So I want you to look at this statement right here. The quickest 75% of the times in 1978 were below the longest 75% of the times in 2003. So going up to your box plot, the quickest 75% of the times in 1978. So here's the minimum. Remember, up to the box is the first 25%. To the line in the box is the next 25%. So we're at the 50% mark, right? Our median. And then to the top of the box is the 75th, the quartile 3, or the 75th percentile. So the quickest 75% in 1978 is all of these values from quartile 3 down to the minimum, because remember, quick for time is a lower time. So that, the quickest 75% of those times is below the longest 75% of the times in 2003. So for the longest 75% starts at quartile 1 and goes all the way up to the maximum. They're talking about the longest 75%. So from 25% all the way up to the top, the maximum. So you can see that there's a gap between these two values, quartile 3 and quartile 1. You could even look up those values. So based on that, okay, the quickest time here, right, we had a lot less wait time in between eruptions, but more variability, less consistency. Whereas in 2003, you had more consistency, but you had to wait longer on average in between eruptions. So based on that, the last question, in which year would you have preferred to be a tourist waiting for the next eruption of Old Faithful? So can you think of one way in 1978 that it would have been preferable, and then a different way in which 2003 would have been preferable? I think I'd rather be in 1978, because even up here at the 75th percentile, we're still waiting less time than most of the 75% or 75% of the times in 2003. But in 2003, one positive could be that, well, you're more consistent, so, you could go and do something else, come back, and you probably make your time to see Old Faithful. But I guess it's a personal decision. So that is just a basic look at how we can use our StatCrunch. We do a little bit of exploratory data analysis and compare means. And now we will go to actually doing some hypothesis testing on the significance of the difference, the observed difference that we are seeing.